Okay, hey folks, how we doing? I'm getting started here on our week 13 content. So this is kind of the point in the semester where I'm going to be skipping around a little bit from various sections in the book. So I'm going to start with this section 21.8 on the Lindemann-Hinshelwood Mechanism. But also in that supplemental document that I shared with you, um, it also describes this Lindemann-Hinshelwood mechanism. So I'm expecting about 3 lectures this week 13 on mechanisms and elementary steps. Some of it will come from the sections in the book. Some of it will come from that supplemental document. And some of it will just come from these notes. Okay, so be aware of that. So this first thing that I want to describe in mechanisms and elementary steps is the very famous Lindemann-Hinshelwood mechanism. And so here you can see I've got it written out in general terms, okay, where A is our reactant, okay, P is our stable product, and M, let me find some more room here, M can be another A, so identical to whatever that A is, or what I'll call an unreactive partner, okay? Unreactive partner. And in this case, we could kind of think of M as a second body. It could also be a third body if I had another reactant in here, okay? So you'll often also hear me refer to that as a third body or a second body, an unreactive partner. So, and an unreactive partner, that means it could be like helium or argon or something like that, okay? So in this mechanism, this describes the thermal unimolecular decomposition of something unstable, okay? So for example, what Lindemann and Hinshelwood worked out was if we have some reaction, okay, something that undergoes what appears to be a first order decomposition. So for example, perhaps A undergoes some thermal decomposition into B plus C, okay, something like that, right? This mechanism really eluded people for quite some time because what they observe is in some limits, it appears to be a first order reaction, but in other limits, it appears to be a second order reaction. So I'm going to actually get rid of this to leave myself more room. So what I want to derive now is why in some cases this thermal decomposition, and really all we're saying, if you think about this mechanism, A undergoes decomposition into product P, right? Well, as it turns out, in order for A to go on and react, like why the hell would A just react on its own? It needs collision with a second body to induce the creation of this excited state. And this unstable, so let's write that down, unstable excited state. And that unstable excited state can then undergo first order decomposition into a stable product, okay? So if we solve for the steady state of A, because as it turns out, this is a really good example of when we can use the steady state approximation, okay? So first we'll note actually the rate of product formation, dp dt, okay? We'll write that as, we recognize that that should be K2 times A star. However, A star, right, it's an unstable excited state. It's going to be really difficult to measure that. So computing the rate of product production is going to be dependent on this rate of excited state formation. So if we apply the steady state approximation, which I want to give myself plenty of room, So I'm going to write d A star dt, okay? And let's go through these reactions, okay? So we recognize that A star appears as a product here in this first reaction. So that's going to be a positive K1 times A times M. So we recognize K1 will actually be a second order rate constant, okay? But now, so that's the forward reaction, but now it is possible that A star can react with this second body and just go right back to forming its stable ground state, okay? So now, and that occurs at rate constant K minus 1, okay? So now we have to kind of view this going backwards, right? So that's a negative rate, okay? And it's going to be negative K minus 1. And then now we can view A star and M as the reactants in the reverse reaction, right? Okay, so that's times A star times M. And then now finally, the excited state appears in a third reaction, so we need a third term. And it's another case where A star is a reactant. So it's going to be a negative rate, negative K2 times A star. And here we recognize K2 will be a first order rate constant. Okay? And when we apply the steady state approximation to this, all of this equals 0. Okay? And so now doing some algebra and solving for the A star concentration, all right, we come up with the following. So all I'm going to do is just solve for A star, right? And so thus we get that the concentration of A star under the steady state approximation, okay, which seems reasonable given that, right, likely forming the excited state is probably slow. And once the excited state forms, it will go on to products quickly. That seems reasonable to make this steady state approximation. That's going to give us the following. K1 times A times M, all divided by K minus 1 times M plus K2. Okay? And now I can substitute this into this rate of product formation. Okay? And so we'll write that in and we'll talk about what happens under certain conditions. Okay? So now if I take all of this for A star and plug it in right here, right? Let's do that. Let's draw a little arrow. It says plug that into right there. I get that now dP dt, so the rate of stable product formation should be K1 times K2 times A times M, all divided by K minus 1 times M plus K2. Let me see what I have on the next slide here. Yes, I gave myself plenty of room to keep talking about this, okay? So now we can see when we look at this product formation, I'm going to put this in a box right here. It's not apparent if this is a first order reaction or a second order reaction, right? If what we're really interested in is what is the rate of this product formation for a thermal decomposition of something,